So hello and welcome to the third Tom Rocks Maths live stream, which I've been doing as part of the Tom Rocks Maths Appeal videos, which we've been releasing over the last few weeks. So like before, I'm going to start off by talking about some of the questions to do with volume that have been sent in by the viewers, so by you guys. So thank you again, as always, for sending in your questions and for sort of taking part in these live streams. So I'll kick off with a few questions. I think I've got 3 questions that I want to talk through that have already been sent in. Then I'm going to talk about a slightly more advanced definition of volume beyond just looking at regular shapes, which hopefully you'll all enjoy. And then we'll open up the live chat like usual for the last 20 minutes or half an hour, and then I'll answer whatever questions people throw in to the chat box. So to kick us off, we had a great question from James, which I think is a really nice reminder of everything we've been talking about to do with volume, which came out on Monday. So James asked, how could we calculate the volume of a flight of stairs? So this is the question, and this is open to a lot of interpretation about, first of all, what does James mean by a flight of stairs? So James, if you're watching, please tell me more about this flight of stairs. Otherwise, I've made an assumption, and we're going to work out the volume of a flight of stairs as I have interpreted your question. So the idea is as follows. We have, what am I going to do here? So I'm going to try and draw a picture. So bear with me on the my, let's say, not great artistic talent. So we need a set of stairs. So what's that going to look like? So I'm going to start off by drawing 2 stairs, and then we're going to build up to a full set. So if I've got a set of stairs, I reckon side on, if you've got 2 steps, it looks like that. And then if I attempt to kind of draw something in 3D, this is where my artistic talent is really tested. I go across and then like that, and we're going to come down. Right, I think that's a pretty good attempt at sort of 2 steps. And so obviously, again, James didn't give any measurements, so I'm going to put down what I think are some reasonable measurements, shall we say. So I'm going to call this thing, well, I say reasonable. These are kind of just made up numbers, but I'm going to say that they're 10 centimeters across this edge. So that's going to mean that each step, we're assuming the steps are regular, so it's the same step throughout. It's going to be 5. This is going to be 5. This is going to be 15. And the height of the step as well is also going to be 5. Right. So this, as I said, is going to be my starting point for James's problem about the volume of a flight of stairs. So if we start off by thinking about the shape that we have at the moment, it's not a regular, well, it is in fact. I say it's not a regular prism. You could actually interpret this as a prism. It's not a regular prism, but it's still a prism because we mentioned in the video talking about volume, we've got a cross section here, the front face, which is the same as you slice through the rest of your shape. So it is indeed going to be a prism. But the way I thought about it was slightly different than the prism method of calculating volumes. So Bobby, in his lesson with us on Monday, explained that normally you would calculate the area of your face, your consistent cross-section, and then you just multiply by the depth or the height as you go backwards into your 3rd dimension. But what I'm actually going to do here is divide it up with this dotted line so that now I've got a cuboid and another cuboid. Because again, Bobby taught us all how to work out the area of a cuboid. It's just width times depth times height. So what we've got then is the smaller one, which is 15 times 5 times 5. So 15 times 5 is 75 times 5 again is going to give us 75 times 5 is 375 centimeters cubed for this front cuboid. And then the back one, so this will have a height of 10 because we're saying the steps are regular, so 5 and then 5. So this height would be 10. So I'm just realized that this is not exactly to scale. This is in centimeters. These are like baby steps, but it's still the right shape. So now this one's got 10, 5, and then going across, we've got 15. So this one is now 10 times 5 times 15. So that's going to give me 750 centimeters cubed. So we add these two together, and then we've got the volume of this set of two stairs. Now, the question from James asked about a full flight of stairs. So I don't know exactly how many steps you would expect in a standard flight of stairs, but if we were to continue this, the way I've interpreted the question again is to just say, well, based on how I've done 2 steps here, so I said this total thing was 10. So based on how I've done 2, the next step is kind of going to have to come in like this. So it can't just be from the top of this one and up. You need some overhang to sort of bolt on the stairs, right? Because there's got to be something to attach it. So I've decided to do it like so. And then we're going to have that one going up and off the top. So to add in a third step, what we're going to be doing is adding in another cuboid here. So this is our third cuboid, but it's exactly the same as cuboid 2. So for every new set of steps that we continue to add in, going up like so, right, and then you're going to get another one. For each one you add, so the 4th one, the 5th one, and we can continue. Each time we're just adding on the same volume as cuboid 2. So the first one is the small one, is 375, and then for every new step, we're adding on the same size cuboid, and that would make 750 for each new step. So then if we added on, like, say, 10 other steps, we just do these 2 plus 10 lots of 750, and that would give us the volume of a set of stairs that looked like what it would kind of go up. Right, so that would be sort of the kind of set of stairs that I've worked out here. Now, there's another interpretation of a set of stairs, which is instead of sort of having it go off the ground, you could have like an old-fashioned set where you want this to go all the way down to the ground, like so. And if we were doing this, then I would just divide this up into several cuboids like so. So this is 1, which we've already done. Then we did 2. So 1 was this one, and this was 2. And then if you're adding in these extra ones and we want to go all the way down to the ground, then what we're doing each time is just adding on 5 centimeters extra piece from the one before. So we started with 15 times 5 times 5, then we went to 10 times 5 times 15. So what we're going to have this time is still 5 and 15, but now another 15. So if I were to rewrite this a little bit clearer, put the numbers in the right places, we always had a 15, we always had a 5, but then we got a 10 for our height for step 2, whereas the height, so if this is the height column here. So we had 5 for step 1, then we went 10 for step 2, then it's going to go to times 15 for step 3, because we made it 5 centimeters taller. 4 is going to be 20. Whoops, that should be up there. 5 is going to be 25. And so we can just then get to be 15 times 5 times 15, 15 times 5 times 20, 15 times 5 times 25. And we can just continue in this way, depending on how many steps we want to add into our system. So we've got 2 types. We've got the ones that are off the floor, kind of the fancy designer stairs, shall we call them, in like a fancy open plan building. And then we've got the old school sort of properly going all the way down to the ground with a firm basis kind of set of stairs. But to calculate the volume, like I said, you could either work out the area of your cross section and then just multiply by the depth. But I think for this instance, it's a bit easier to just divide it up into several cuboids and then just add up the volume of all those cuboids. So thank you, James, for the question. That hopefully has answered how to calculate the volume of a set of stairs. Great little, like, fun, I guess, sort of throwaway question, but reasonably interestingly. So the next question I wanted to go on to, so this one came in from Chen Ying. So thank you, Chen Ying, for your question. This one is like a puzzle. And I'm a big fan of puzzles, as all mathematicians are. We love solving puzzles. So this puzzle asks us about doubling the volume of a cube. So we're going to start with a cube. And then the question is, how do we modify the cube so that we get double the volume? So imagine we were trying to build a new cube. Oh, getting tangled in my wire. Build a new cube that was twice the volume of our original cube. So first of all, we'll start with a cube. So again, artistic talent or lack of. Oh, that's not too bad. Right, so we've got a cube. I'm going to assume this has side length 1 everywhere, because then it makes it easy to know the volume. So the volume of our cube is just going to be equal to 1, isn't it? Volume. Because again, from Bobby's lesson in the video from Monday, it's just length times depth times height. So for a cube, they're all the same. So this is just 1 cubed, which is 1. Now, if we double the volume of this cube, then the new volume has to be 2. And the question is, what is going to be the side length of our new cube so that we get a volume of 2? So there are a few ways of thinking about this. By making this side length 1, I think I've made the problem easier than it could perhaps otherwise be. So I should probably go back and sort of give you the harder version and then say that we're going to do this. So if we had this as just some general length a, then our volume would be a cubed. Right? And then we want a new volume, which would be 2a cubed. And this is usually how a problem like this would be stated. And then, as I said, you could simplify it yourselves by making a 1, because it doesn't really matter. It's still twice the volume. So the trap to be careful not to fall into on questions like this, where you're doubling volumes or areas, is that we're definitely not doubling the side length of the cube. So that's sort of perhaps the first thing that might come to mind. I'm trying to double the volume of a shape, so just make everything twice as big. But of course, that's not going to work for a cube, because if we tried that, as an example, draw a new cube where everything was 2a. So 2a, 2a, and 2a. Then our new volume is 2a times 2a times 2a. So then that's equal to 2 times 2 times 2a cubed. In other words, 8a cubed. So doubling the side length of a cube gives you 8 times the volume because of this cubed factor. So when you introduce the 2, you've actually introduced it cubed, right? Because it's coming in 3 of our lengths. So what that's going to mean back here is our new volume, 2a cubed, this has to be equal to the new side length x cubed. No matter what x is, we can just say, right, this is our new volume in terms of the old one, but it has to satisfy the volume of a cube, which is just 3 lots of the side length. So we can then just solve this equation. So doing that and taking the cube roots of both sides, this is just going to tell you, that taking cube roots, we're going to get x is equal to a, and then in front of that, we're going to have the cube root of 2. And that is going to be the answer that we needed. So this was a lot easier, as I said, when you made this 1, because if you make a 1, this is 1, this is just 2, and it's hopefully a bit easier to see straight away that the cube root of 2 is the new length that you need. And this will work in any dimension. So if you're doubling an area, then you're not multiplying, doubling a square, you're not creating a new square of side length 2, you're creating a new square of side length square root of 2. So it's an important thing to remember in all of these different dimensional problems. Okay, so thank you, Chen Ying, for that question. Now, the third one that I particularly liked was sent in by 2 people. This one came in from Joe and Jamie. I assume this was sort of a joint question. And they talked about something called the Menger sponge. And they wanted to know what the volume is for the Menger sponge. Now, this is an awesome question. You obviously have to know what the Menger sponge is to be able to figure out what's going on in this question. So we're going to have to start there. What is a Menger sponge? So it's defined as follows. Menger sponge. So before we get to so this is a three-dimensional shape. It's in fact a fractal. Now, some of you may have heard of fractals. Some of you may have not. Don't worry if you haven't, but it is going to be a three-dimensional fractal. And to think about how to define it, I think it's best if we start by thinking about the 2D equivalent and then extending that into 3 dimensions. Because 2D is a bit more intuitive to start with, easier for me to draw, and then we can think about how it might work in those 3 dimensions. So our starting point will be one face of the cube. So the Menger sponge kind of looks like a cube. Should have mentioned that. So if we're thinking about the 2D simpler case, we're going to take the square. And what you do to create your Menger sponge or the 2D version is you take your square, you divide it up into 9 equal squares, like so. I'm going to redraw this because I'm going to need a really big picture to be able to draw this so you can all see what's happening. So let's do a really big square as our starting point. Right, so then we have, that goes across there. So the starting point, remember, was to divide up our square into 9 equal squares. Mine may look more like rectangles, but they're meant to be squares. Now, the first thing you do is you get rid of the middle square. So I'm coloring it in to show that it's being deleted. So we are now left with 8 squares from our original one. 8/9 of the original area, you could think of it as. And that's going to be quite a helpful thing for when we're coming to the volume later. Now, to generate a fractal, one way to generate a fractal is to repeat the same procedure over and over again on a smaller and smaller scale. So it's called like an iterative procedure because you are iterating this several times again and again and again. So what we want to do is on each of the 8 smaller squares, do the exact same process. So we divide up this square into 9 and we delete the middle one. We divide this one up into 9 and delete the middle one. We divide this one up into 9, delete the middle one. So I will do it on all of them just to make it complete. I won't for the next step, but for this one I will go through the pain of drawing lots of squares. Delete the middle one, divide up into 9, delete the middle one, divide up into 9, delete the middle one. Now, we have a much more complicated looking sort of 2D Menger sponge. And what we want to do now is, again, repeat the same process. So it's an iterative fractal, an iterative procedure. So we're going to do the exact same thing, divide up each of the squares into 9 pieces and delete the middle. Each of the squares, 9 pieces, delete the middle. So I'm just going to draw it in this top one. Definitely not doing it for the others, but you would do this in all of the squares. Right, so imagine this top one copied into all of the other ones as well. And then you're just going to keep going again. So you then take all of these squares, divide each of them up into 9, and repeat. And the same for every single square on here. So this is like, you can think of it as one face of our Menger sponge. So the Menger sponge is the 2D equivalent of this shape. So how best to do this? So I can I'll draw a small picture and then we'll come back to this one. So if I try to draw a cube. So we started off with our square, dividing it up into 9 equal squares. So we want to do the same with the cube. And you can think of it, as I mentioned, as doing this on each face. So if we go over to our cube, let's divide this up into 9 squares on this face. But again, we're in 3D. So if we're doing this on all of the faces, like so, again, testing out my artistic. You really need to be good at drawing to be a mathematician. I have discovered this. So I've divided up each of my faces into 9 squares. So now I want to know how many cubes have I divided up my one original cube into. So I'll give you all a few minutes to think about that. So each face has 9 squares, and I want to know how many cubes I've divided up the original cube into. Also, hello to everybody who's typing hello. So if it helps, you can imagine trying to build the sponge yourself, or trying to build this shape yourself using smaller pieces. How many pieces, how many small squares have we used to make the bigger one? Is another way to think about it. Awesome, well done, Sam. Thank you. So the answer is 27, as Sam has said. So the way I like to think about it is you've got like 3 sections. You've got the first slice, then you've got this second slice here, and then the third one at the back, and each of them contain 9. So it's like 9, 18, 27. So we've got 27 cubes over here. Now, what we're going to do next is the same thing we did for the 2D square, but we want to do it on our 3D cube, because the Menger sponge is this on a cube. That's how you define it. So what that's going to mean is we need to remove this one. So this square has gone. We need to then remove the square over here, the square on the top, and the same square, the middle square, on the other 3 sides. So your cube has 6 faces, and you're removing the middle square, think of it, or the middle cube, from each of your 6 faces. But there's also a final one right in the center. So the very center of the cube is another cube that you have to remove. So you're building, it's a cube at step 1. You have a cube, but you've like got a hole here, and then it kind of goes back all the way to the far side and also goes up and down and out. So you've kind of got like a plus sign shaped hole in the center of your cube. It's a bit tricky to visualize without having basically little cubes to build and play with. I really should get some little toys that I can show this. But you're removing 1 cube from each side in the center, and then the very, very central cube right in the middle of everything. So you're removing a total of 7 cubes. So, and that's going to be important. So we've got, so the question from Joe and Jamie was, what is the volume of the Menger sponge? That was the question, because we're talking about volumes in this particular topic. So, volumes of fractals. Christ, this is pretty advanced stuff. So we started with 27 cubes at step 1. And then we reduced this down to be smaller and smaller and smaller. And we did that by removing 7 from the 27. So you can think of it as, what's the best way to think of this? Of step 0, our volume was equal to 1. So assuming my original cube had volume 1. Then we divided everything up into a third, a third, a third everywhere. And so the number, first of all, in fact, the number of cubes remaining, we then turned it into 27 cubes. So we had volume 1. I probably should write a proper table. Okay, so we want, this is going to be the step. Then we want to know the number of cubes. And then we want to think about what the volume will be, perhaps. Yes. Okay, so step 0, we had 1 cube, and the volume is 1. Step 1, we had originally 27 cubes. We've removed 7, 1 from the center of each side, plus the 1 right in the middle of everything. So we removed 7, so we're left with 20 cubes. And we can wonder about what the volume will be. So we had, well, we know what the volume will be because we've got 20 cubes left, and each cube is now 1/3 on each side because it was dividing up each length into 3. So the volume is 1/3 cubed. So this is now, so the third, so we got 1/3 cubed. Let's just write it over here. The volume is 1/3 times 1/3 times 1/3, which is 1/27. But then we've got 20 of them, so this is 20/27. Right, we're going to do the same thing again for the next step. So like we did with our 2D version, we're going to divide up each of these into 9 smaller cubes, remove the central one and that central one of the whole cube. So again, divide each cube up into 27 smaller ones and remove 7 of those 27. So what you're going to see is that if your step is at step n, we have 20 to the n cubes, and each of those cubes is 1/27 to the n in volume, I think. Let me double check that. Yes, it will, won't it? It will indeed be 1/27 to the power n. So at step n, this is 20/27 to the power n. So this is your volume at step n. So this works for the first 2. You can calculate the next one, and you'll get your final, the right value given what step you're at. So the volume at step n of the Menger sponge is 20 divided by 27 to the n. So the Menger sponge itself is actually this final cube when you do this forever. So a fractal will continue forever. You repeat your process again and again and again. Gets sort of, you're kind of removing more and more bits of your cube. So even though you can think of it like it still feels like there should be something there, but our formula for the volume at step n is 20/27. So if we let n go to infinity, what will the volume do? That's what we want to know. So we want to take the limit as n goes to infinity, repeat this again and again and again, right the way through to create the whole fractal. And we want to know what that is going to be equal to. And that will be the final value of the volume for our Menger sponge. Exactly, Sam. It's going to go to 0. So the reason it will go to 0 is you've got here 20/27. This is a number smaller than 1. So anytime you have a number smaller than 1 and you multiply it by itself again and again and again and again, it gets smaller and smaller and smaller. So I often think about, say, the number 1/2. 1/2 times 1/2 is 1/4. Times 1/2 again is 1/8. Then it's 1/16, 1/32. It's getting smaller and smaller and smaller and going to 0. So this limit will be, well, I guess we'll tend to infinity as n goes to infinity. No, not infinity. Not infinity. N's going to infinity. The volume is going to 0 because it's less than 1. Getting ahead of myself. So the volume of this Menger sponge is 0, which is crazy, right? This is how crazy fractals are. Now, if you think about the surface area of the shape, so the surface area of a cube, surface area of a cube is just going to be the area of each face, which is A and A. So the area of one face is A squared. There are 6 of them. So the surface area of a cube is 6A squared. Now, if you do this, if you work out the surface area for the Menger sponge, this fractal using this process that we've talked through, your surface area formula, and I'm not going to go through this because this was a lesson on volume and I want to get on to my other question. But if you calculate the surface area for your Menger sponge, the surface area is equal to 2 times 20 over 9 to the n plus 4 times 8 over 9 to the n. So for this, so the volume is going to 0 over here. Volume goes to 0 as we create the full fractal and let n go to infinity. But the surface area is equal to 20 divided by 9. So that's bigger than 1. It's bigger than 2, in fact, to the power n. So as we let n go to infinity, this goes to infinity. Because it's a number bigger than 1 to a higher and higher power, this goes to infinity. This bit will go to 0, but this bit goes to infinity. So the surface area altogether tends to infinity. So this is why the Menger sponge is a fractal, because fractals exhibit this kind of sort of almost unbelievable behavior. So the Menger sponge fractal has 0 volume, but has infinite surface area. So that was an excellent question, Joe and Jamie. Thank you for sending that one in. Right, which brings me on to the final thing I wanted to discuss. So this is now, thank you to everyone for your questions that were sent in before. I've covered a few of those. So now I'm going to talk to a slightly more advanced way of thinking about volume, and then we'll open up the chat to some questions that I'll try and do live for you all. So I'll just clean the board. Got too much chalk dust on my dusters. Okay, so the final topic, or the more advanced topic I wanted to mention in this context of volumes was how to work out the volume of a non-regular prism. So in our lesson with the Tom Rock's Maths Appeal series, we talked about having a regular cross-section. So for example, you could have a triangle and then you extend that into 3D to create your triangular prism. Or, you have your circle, you extend into 3D to get your cylinder. But the question is, what if this part of the shape, what if here we allow some kind of sort of, I guess, curve or something? What if we allow like a non-regular shape to happen within our sort of prism or our solid? So the next, I guess, logical step after looking at regular prisms would be to look at something that we call volumes of revolution. So this is what we're talking about next, volumes of revolution. Now, this is definitely a more advanced topic than GCSE Maths. This is something you will meet at A-level Maths. So when you're sort of 17, 18, if you're in a different country that's not the UK. So we want to think about volumes of revolution. But I think they're pretty understandable if you approach this in the manner I'm going to demonstrate for you all. Now, the idea here is I'm going to have start with a graph of something. So this is my y-axis, and this is my x-axis. And then the idea is I'm going to have y as some function of x. So let's suppose I just have, it doesn't really, well, I want something I can draw. Let's do something I could draw. What if it looks like that? Okay, so there is a function. So this is y as a function of x. Now, a volume of revolution is formed by taking your curve and rotating it around an axis. So you've got two axes which we can rotate around. So I could rotate around the y-axis and create a three-dimensional shape, or I could rotate around the x-axis and create a different three-dimensional shape. So I want to concentrate on the x-axis rotation for this particular example. So I'm going to take my graph and I'm going to rotate it around this axis. So as I do that, it creates a sort of circular shape here, and then this comes in, and then you create a circular shape here. So this would be an example. It's kind of like, this one kind of looks like a horn, like a trumpet horn you would blow down. So you've taken your graph, which was here. So this here is our original like graph. And then we've just rotated around the x-axis. So we've just gone like that around the x-axis to create this three-dimensional shape. Now, what we want to know is how do we calculate the volume of this particular shape? And I should stress here, this could be any shape. So I've drawn a quite simple one, but you could have any graph here, which, so let's suppose it, I don't know, said it looks something like this. And then when you create your three-dimensional rotation, you still get this sort of weird 3D, right? So it's kind of like a cylinder, but with this big bump in the middle, right? So I don't know what you would call that shape, but you can literally have any shape graph here, and then you just rotate it around your axis to create what we call a volume of revolution. So to work out the volume of a revolution, we have to go back to something I was talking about in the second live stream, the one a week ago, which was about thinking about doing integration and sort of working out areas. We talked there about working about areas, and here we're going to apply it to volumes. So the first step in thinking about what this formula might look like and where it comes from is to take a slice through my curve. So we know that we've rotated around the x-axis, and I'm just going to take, imagine just taking two big knives and just slicing it at some point. So I could slice here, I could slice down here, you know, wherever. Now, as I take a slice, the first slice in pink, kind of, you have a bit of a slant, and then you have a circle, and you have a circle, and then here you also have a bit of a slant, don't you? Right, so something like that, and then down here, it's a bit smaller, but again, you've got a circle at that end and a circle at that end. Now, like I mentioned again last time when we talked about integrals, the idea was you took your slices thinner and thinner and thinner and thinner. So you're doing a limiting process to make these really, really thin and then add them all up together. So if we do that here, if we take these as thinner and thinner slices, this shape will look more and more like a cylinder. Okay, so at the moment, the first big one has, you know, there's a bit of a slant here. So it's not quite a cylinder. But if we take thinner and thinner slices, so they're almost like infinitely small, really, really small, thin slices, they look like incredibly thin cylinders. And that's going to be the key way to think about how to calculate the volume. So let's just suppose, so it's going to look like this. So let's work on this shape. Okay, so we've got a really, really thin cylinder. Now the volume of a cylinder, so cylinder volume, is equal to, well, hopefully we all remember this from Monday's lesson, pi times the radius squared times the height. So going down to our slice down here, so we've got pi, definitely. Now the radius squared, so the radius is the distance here on our cylinder. So looking at my graph, my radius is the distance from the x-axis, which is in the center of my shape, to the edge of my graph. And again, it'll be here and it'll be up here. So the radius is changing. This is why this is not a cylinder, because my radius changes as I move along the shape. And the same happens over here. The radius is going to increase and then decrease. But the way we describe the radius is actually just the distance from the x-axis to the graph. But we've said that's y. So at this point, this has value y. This has, the value y, where y is your function of x. So whatever function describes this graph, the radius is given by y. It's the height at that point. So this, in fact, is just y squared. Now, the final part is to think about the height. So we've got pi times y squared. So again here, this will be y, where y was the distance up here. And then the height is this little bit here. This is our height. So I mentioned that we're going to take smaller and smaller, thinner and thinner slices to get a more and more accurate set of cylinders, and then we add them all together. So each slice of cylinder we take has a different radius, where the radius is just the value of y along the graph. So each slice can have a different radius. But if we say the width of one slice is dx, and then we let dx tend to 0, then this is equal to dx, and then we just need to add all of these up. So the volume is the sum, so we're adding all of them up, of pi radius squared times the height, where the height is this really small dx. So now, just like with our integral, I'll rub off my fun-looking graph. So just like with our integral, what we want to do now is actually do this limiting process and let the dx go to 0. So the limit as dx goes to 0 of this sum, pi y squared dx. So that actually then just gives you the integral of pi y squared with respect to x, where we're integrating from the value here, a, to the value here, b. So this is b, and this is a. So the volume of a revolution is equal to, whoops, come right through the middle of the integral. Won't bother with the box. The volume of a surface, surface or volume of revolution is equal to the integral from a to b in the x direction, so the integral along our graph, times pi times the radius squared, where the radius is the value y, so that's the actual function of our graph, and then we have the dx, because we're adding all of these up over the length of the whole thing. So this is the formula that you are just taught, or you are told when you study volumes of revolution, but it actually comes from doing the geometry and just from working out and adding up the volume of lots of little cylinders, where you just make them thinner and thinner and thinner, and then add them all together, taking the limit to get your integral. Right, and then you can plug in any function you want for y as a function of x, and that will work out the volume for you. Okay, so I'm going to open it up to questions in the live chat now. So I've answered, we started off with some discussions about cuboids, and I was looking at the volume of stairs. Then we talked about doubling the volume of a cube. Then we moved on to fractals and looked at the Menger sponge, which had 0 volume but infinite surface area, which still blows my mind. And now I've just sort of given you a whistle-stop tour of how volumes of revolutions work. Okay, so I'm just going to rub the board while you guys get thinking of some questions. Right. So Sam has asked me, how would I work out the area of a torus? So you can do this, but it requires some pretty advanced multivariable calculus. So I'm not sure I really want to go into the full three-dimensional integral and parameterization of a torus that would be needed to answer that question. But I will at least draw a torus and talk about a torus because toruses are cool. So the torus is basically the mathematical name for a donut. So which I can't draw. So what we've got here is I attempt. So this is my sort of attempt at trying to draw a torus. So it's like your donut, right? So this is the hole in my donut. I'm trying to make this look a bit 3D as you look from the side. And then this obviously goes all the way around. So it's very hard to draw a torus, but it's basically just think of it as a donut. Now, rather than, as I said, rather than going to the way to calculate the area or the volume, which requires double and triple integrals and lots of very complicated multivariable calculus, I actually did this question with my first year Oxford students this week in one of our tutorials. So it's pretty hard stuff. So an interesting way or thing to think about with a torus is how you might describe the shape mathematically. So the way we do this is if we picture viewing it from above to start with. So looking down on the torus, it looks like, so this is now in the XY plane. So this is in 3D, X, Y, Z, right? But Z is up here, Y is over there, and X is that way. But now if we look down from above, it just looks like there's a circle in the middle and there's a circle on the outside, right? So looking at a donut from above, you've all probably done this at some point in your lives. This is what it looks like. So the way to describe a torus then is to think about, well, kind of how might we describe the torus with an equation? So we can think about how to describe the equation of a circle. So does anyone know the equation in X and Y that we use to describe a circle? So if you do, pop it in the chat. Awesome, thank you, Pascal. X squared plus y squared equals the radius, is radius squared. So the equation of a circle is x squared plus y squared is the radius squared. That's how we describe a circle in the xy plane. So when you're doing your torus, what you've kind of got here is you've got one circle. Let's say this radius in here is A. And then let's say, wait, how do we... I don't do it like that, do I? Or do I? Let me think. Just trying to make sure I define this how we normally define torus is. So we want that, and then we want that. So if I put that one in. Okay, and then I call... Right, so if I say this occurs at some distance b, this inner circle, which is going to be halfway between the hole and the outside bit, then what we do is we say this distance here, or here, I guess, is b plus a. And then this middle one here is going to be, inner one is b minus a. So the inner circle, I guess, so the inner circle is x squared minus y squared. Whoops, x squared plus y squared is b minus a. And the outer circle is given by x squared plus y squared equals b plus a. Right. So that's kind of the starting point and the way that we define this viewed from above. And then when you want to define this now in 3 dimensions, I have to remember how to do this. I think it looks something like x is equal to b plus a cos theta, b plus a cos theta times, oh, I'm going to forget what's y and what's z. Z has got to be, z has to be, what does it have to be? So I need to satisfy, z needs to be, I think it can't be that. I can't remember. It's embarrassing, isn't it? I did this earlier in the week. Let me find my notes from my my tutorial that I did. Fortunately, is right in front of me. Right, here we go. I've got it now. I think. Yes, that's wrong. I've written the wrong thing. That's a sine. I knew I was doing something wrong. So for your torus, you say that x is b plus a sine theta multiplied by cos phi. That's it. Then y is b plus a sine theta multiplied by sine phi. And then your z component is a cos theta. Right. That's how we do it. Okay, so this gives you your torus in 3 dimensions, which is a parameterization, and then you use that in your integral to work out the area to answer your question, Sam. So thinking about what's going on here, because I'm aware I just pulled this out of thin air and I forgot the equation anyway, because it's fiddly, as you can see. So the reason I wanted to think about what it looks like from above was to just get you to think about the fact that you've got this b plus a and b minus a as these 2 different radiuses for your inner circle and your outer circle. And the actual torus itself is happening between the 2, right? So it's like the donut shape in 2D and then our 3D donut over here. So what's going on down here is we are introducing 2 different angles which are parameterizing our shape. So the way to think about this is this central point. So this is like your circle, your slice through your donut. And then this point here is going to be given, this has radius A, right? Based on our picture from above, the outer circle has radius A. So this thing here has radius A, and to capture that it's a circle, we have this angle theta. So theta is the rotation around this circle, this like slice through your donut. And then phi, the other angle, phi represents this way around. So you can sort of think of it as, you start, say here, phi tells you how far around to go, around your donut. And then theta tells you how much to go sort of up or down within that sort of tube bit that you're inside. Like I said, it's pretty advanced and it's pretty difficult to think about, and does require, to calculate the actual area, does require integrating these functions over 2 dimensions. So I'm definitely not going to do that. I'm going to leave it there. Not the best explanation I've ever given of a torus, but hopefully gives you a feel for how we try to investigate these. I think the takeaway message would be this idea of the 2 angles. So you've got theta here and phi as the big one. Phi tells you how far around your donut, and theta is how far up or down. All right, any other questions? Thank you, Sam. That was a tough one. I mean, if nobody else has any other questions, I can always just talk about another example of a volume of revolution. Or I have many other questions that were sent to me, but I think it's always fun to at least give you the opportunity to interact live as you guys have tuned in live rather than late on. Is there a thing for torus's sections? not entirely sure what you mean by that question. Possibly due to my very confusing explanation of what a torus is. Well, in the meantime, I will clean the board. So we have got time for about one more question. Anybody has anything they want to know? Doesn't have to be related to volume at this point. I think we've talked a lot about different volumes and ways of thinking about volumes. Okay, so what have we got? The area under y equals e to the x is e to the x is the volume of its revolution, also e to the x. Great question, Sam. Right, let's do that. That can be our final thing to finish it. You're on form today, Sam, with these questions. So I mentioned earlier the volume of revolution. So just to remind us, the formula was we had pi, we had the integral from a to b, our 2 points, then we had y squared, and then we had dx. So if we're thinking about e to the x, right, so e to the x looks like this between 0 and infinity. Okay, and then it will decrease over here, right, as well. So let me think about where we want to do our volume. Right, so this is y equals e to the x, and this is x. So let's just leave it as a and b for now, and then we'll worry about the limits in a minute. So if we plug in these numbers, we expect the volume to be pi ab y squared, so that's just e to the 2x dx. Now this is not going to just give us e to the x, so it's definitely not quite what you thought earlier, Sam. So whilst the area might, or the function itself might integrate to give you e to the x, when you're doing this volume of revolution, and we take this around here and this around here. So again, this is like an infinitely long horn, right, where you're blowing down this end and the sound's sort of coming out down here. So calculating this, you're going to get pi. You're going to do your integration, so that's going to be a half e to the 2x, because if I differentiate that, the 2 comes down to cancel the half and gives me e to the 2x between b and a. And so that's now going to be pi over 2 times e to the 2b minus e to the 2a. Right, so that's our formula for 2 general points a and b. So if we now think about right, so we've got pi y squared dx, yep, pi over 2. And so if we now plug in the values, we can think about what a and b might be. So if a was going all the way down to minus infinity, then e to the minus infinity would give us 0. So that term's going to vanish if we went all the way down to minus infinity. But then if we went all the way up to positive infinity, this one goes to infinity. So if you were working out the volume of the whole infinitely long horn shape going like this, you're going to get infinity, which perhaps isn't a surprise because it's an infinitely long shape and it's growing in height as you go further and further along x. So you would get infinity for the full shape. So instead of doing that, let's say we do it from minus infinity to 0. So let's look at the volume of this half, just the negative x values. So if we plug those in, then that's going to tell us now that a is minus infinity and b is now 0. So then the answer there will be pi over 2 times e to the 0, which is 1, times e to the minus infinity, which is going to give us 0. So the answer for this part, only for negative x, the answer is pi over 2, which is a really nice, perhaps surprising result. We have an infinitely long section, which has a radius 1, and obviously down at infinity it goes to 0. But it's infinitely long, and yet the volume of this section is equal to pi over 2. So great question, Sam. Not quite perhaps the answer that you had in mind or were looking for, but certainly an interesting thing to think about. So the full graph would give us infinity, but the negative bit gives us pi over 2, which is a really nice result, I think. Right, so that's just gone over an hour, so I'm going to call it a day there. Thank you again, everyone, for joining me. Thanks to everyone for sending in your questions. So we had James talked about the volume of a flight of stairs. Great question, James. We had Joe and Jamie maybe talk about fractals and the volume of the Menger sponge. So remember, for those of you just joining, we showed that the volume of the Menger sponge, which is a 3D fractal, the volume is 0 and the surface area is infinity, which is mind-blowing. But we wrote down some formulas and we showed it was true. And then we also looked at doubling the volume of a cube. That was our other volume question. Then I went on to talk about volumes of revolution. So I derived this formula geometrically and sort of thinking about adding up lots of cylinders. Then we've done this example here with the exponential. And I also talked a little bit, though it was quite muddled, but I talked a little bit about a torus and how you think about a donut and describing that in three-dimensional space. So again, thank you everyone for joining. I'll be back in exactly 1 week, so 4 p.m. UK time next Friday. And the theme will be straight line graphs. So there's a lot of fun we can have with straight line graphs. So the next Tom Rocks Maths Appeal video will come out on Monday. That will be me, Bobby, and Susan explaining straight line graphs. Then Bobby and Susan will do their questions on Thursday. They record those in a video. So if you have any questions for Bobby and Susan, send those in by Wednesday. And then I'll be back live 4 o'clock next Friday, UK time, to answer questions people have sent me beforehand. So again, I'll start with questions that have already been sent in, and then I'll open it up to the live chat. So thank you very much, everybody, for joining me, and I'll see you soon. Bye.